So following on from the previous two videos, we got to this stage here. So as x tends towards infinity, it will head towards 1. As x tends towards negative infinity, it will also head towards 1. But here's the thing: we know that as you approach -7 from the left-hand side, it will head towards positive infinity. But then looking at this part of the graph, how do we know it won't do this? So you've got a graph looking like this. How do we know it won't overshoot and then come back up again and then heads towards 1? You see, our natural instinct would just be to just join these two up in a smooth fashion like this. Okay, that's our natural instinct. But how do we know that it won't do something like this? From infinity, how do we know it won't do something like how do we know it won't do something like this? It will overshoot and then come back up again and then head towards 1. How do we know it won't do this? You see, the reason why we know that it won't do this is because if you look at the first derivative of this, in the first video, the first derivative was something. It was this here, plus 7 squared. It was something like this. We know that this thing can never be 0. It's always positive. This thing's always positive, meaning that, hang on, the reason why we know that it will never do this here is because if you look at the first derivative is never 0. But if you were to do this here, then the first derivative, there must exist somewhere in the first derivative where it must be 0. But in order for the graph to do something like this, there must be a turning point. There must be a turning point, meaning that in the first derivative, somewhere in the first derivative, it must equal 0. But then when you differentiate this here, hang on, let's differentiate this. So let's now differentiate this. Okay. So in the first video, I gave you a long method of differentiating this. But whenever you try and differentiate a quotient like this here, rewrite it as this. Rewrite it as this. So you've got plus 2 and then -2. This is a trick. Merge these two together. That would give you 7. So what you've got here is this thing here. Take away 2, and then can you see these two are now the same? So that will then become this. Okay, so normally normally you would do something like this. Write it as a product of two things to the power -1, and then you would differentiate this. But the trick here, when you differentiate, when you're faced with something like this, rewrite it as this here. Okay, so when you differentiate this will be 0. So you can just concentrate on differentiating this. It's a lot easier than trying to differentiate this thing here. Okay, so well, anyway, when you differentiate it, when you come to this bit here, visualize this bit here as this. So here, this thing gets multiplied. Well, blah blah blah. The derivative will be this. Tidy it up, it will then give you this. Okay. So far, so actually, this is our first derivative. Earlier I said it was 1 over x plus 7 squared. This is wrong. This is our first derivative. Okay. So far this is our original function here. This is our derivative. Okay. And now when we have our first derivative in front of us, we can see that it will never do something like this. It will never do something like this. Overshoot and then come back up again. It will never do this, because in order for it to do this here, there must exist there's a turning point. So somewhere in the first derivative, there must exist a point where this thing here equals 0. But then if you look at it, this thing here would never equal 0. It's always greater. It's always greater than 0. So f prime is always greater than 0. So it will never do anything like this. It will never do this. It will never do this either. And then because here there must exist two turning points. Here it will never do this. Here it must exist a turning point. But if there exists a turning point, that implies that f prime must somewhere f prime must equal 0. But looking at this, f prime is never 0. Okay, so we know that it must do this. Okay, and another important thing is that a lot of people think that if f prime, if the gradient is always greater than 0, it implies that it means that that f, the normal function, is always increasing. A lot of people think this. If the gradient, a lot of people think that if the gradient is always greater than 0, it must mean that it must mean the graph is always increasing. So for example, if you try and create a graph where the gradient is always greater than 1, so a gradient, a graph, if you try and draw a graph where the gradient is always greater than 1, you see this here is no good because here the gradient is negative. Okay, if you try and create a graph where the gradient is always positive, so most people think that, sorry, this here is negative now, so this here is no good. If you try and create a graph where the gradient is always positive, well, a lot of people think that it's always increasing, because if you try to draw a graph where the gradient is always bigger than 0, a lot of people will think that f of x will always increase, but it's not the case, because if you look at our graph here, remember our graph is this. Hang on, let me just fill this in. Our graph is like this. You see, our graph here, our derivative here is always increasing. Sorry, our derivative here is always positive, meaning that the function here, well, is climbing. But the thing is, f. Well, hang on. Down here, a lot of people think that if the gradient is always positive, then this must always be increasing. But our graph here is not always increasing. Look at this. Our graph here is going up. So let's say this point here is 10. But then when you get to -6, it's somewhere down here. So it's decreasing. So this statement is not true. Okay, this statement here is not true. It's not true. A lot of people think that. The reason why is, well, if you try and draw a graph where the gradient is always greater than 0, your graph, yes, it does. This seems to be true. F is always increasing. It seems to be true, because when we try and do it, here you cannot do this. This is a negative gradient. If you try and do it, it's always increasing. But then in our case here, it's not true, because here yes, if you look at our gradient is always increasing. Look, positive gradient, and look, positive gradient. Our gradient is always positive, but yet our our normal function is not always increasing. Look, it's looking at this here, it's above 1, 7, 10, 20, 100, and whatever, but then down here it's negative now. You see, so this here is not true. This here is not true. Okay, in our case, it's not true. In our case, our gradient's increasing. Sorry, our gradient is always positive, but our function is not always climbing. You see, it's climbing here, and then it decreases, and then it climbs. But the point here I'm trying to make is that this point here is bigger than this point here. Okay, so this statement here is not true. This statement here is not true. Okay.